You are welcome to this lecture. We are talking about the plate fin type heat exchangers, and we will now today in this class we will try to talk about the stacking pattern or the layer stacking pattern in a plate fin type heat exchangers. And we have this is particularly important for multi-stream fluid heat exchanger, or though it is equally important in case of two stream exchanger also, because in a two stream heat exchanger also it is not that it is limited between only two fluids, that two fluids are again divided into number of layers. So, it may be such that we have two streams, fluid A and fluid B, then this fluid A and fluid B again are stacked in different layers like AB, 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 and now we have in context to one of the problems, we said that these AB layers, when we arrange them together, we put them in a what is called we put it in if this AB configuration, if we have say fluid number A and fluid B, one of them is say hot and one of them is cold. So, we said that while arranging them in a plate fin configuration, we put them in alternative, usually alternative hot and cold condition, and then we put them in this sequence A, B, then A, then A, and then in between we have say this is B and we have B, and we said that this we always try to put a symmetry between this pattern. Ideally it should have been AB, AB, and so on like AB, it should end with AB, but generally what happens, we put another layer at the end. And why do we put that one? To give a symmetry in this type of configuration. So, that we will now try to learn in this class, and particularly when it is several streams, we have like A, B, and say C and D, like that. So, we have different combinations, like someone can put it A, B, then D, C, and that would be the repetitive one, A, B, D, C, and someone may think like putting them in some other combination, say B, C, A, D, B, C, A, D, like that, or some other combination. So, there are different type of layer that would it would result. So, often we have to find out what is the optimum layer stacking pattern. So, as you can understand that this becomes a design problem to find out an optimum layer. Which optimum layer, or which is the criteria to tell that this is an optimum layer or this is the best layer. So, we have to decide some kind of criteria which will correspond to the optimum layer stacking pattern, or sometimes the fluid flow also decides whether we will be using say a double layer A, B, then C, D, and generally what happens, this repetition is to accommodate a very high flow rate fluid, and then we may again we have A, B, C, D, just to accommodate more amount of fluid in a particular for a particular stream. But otherwise if it is not so, if it is just a B, C, D or A, B, C, D, E, or even some other number of fluid streams, we need to find out what is the optimum layer stacking pattern. So, in that context we will see that say in a multiple fluid stream arrangement, we may have to arrange in say A like then some fluid moving in this side and some fluid is flowing this way, and this is this moving out this side, moving out, coming in, moving out, and in general it is all the fluid streams, or rather the hot fluid streams we put from one end, and the cold fluid stream we put them in another side. And as we can understand that it is it may be such that we may have some fluid stream which is not really belongs to the hot one or the cold one. So, we may have to look for an exact intermediate position where it will have an entry, and depending on the its desired exit temperature, we may have to take it out earlier, or we may have to put it at some intermediate locations. So, otherwise if we keep this option aside at this moment, that we are not having intermediate entry and exit, but we have clearly some fluid streams where we can distinguish that this is a hot stream and this is a cold stream. How are we going to arrange them to have an optimum layer stacking pattern, we can call it. So, let us look into that first, and if we actually we will try to show it with an example. Like here we have say this is a 5 fluid stream. In this 5 fluid stream, some of them are cold stream, as you can understand that the fluid stream, we have 5 fluid streams, out of which this A and this E and this B, they are clearly, these are the entry temperature, and we are not say we will not look into this optimum arrangement. This is in context to the I mean situation where we have applied the genetic algorithm to find out the optimum arrangement, but just first of all we look into this problem where we have clearly 3 cold fluid stream and there are 2 hot fluid stream which are entering at 300, whereas these cold fluid streams are entering at one at 700, another one at 180, the third one is also again entering at 160. So, these are clearly the cold streams, this 170, 180 and 160, they are the cold side streams, and the other 2 are the hot streams. Now, if we apply that as we told that if we solve that simulation problem that we have discussed in the earlier classes, that multi-stream plate fin heat exchanger algorithm will give us the exit temperature corresponding to this. So, the B will come out at 214, then C 265, so on, and these are the exit temperature for this fluid streams. Now, we also know the mass flow rate of these fluid streams and the Cp of these fluid streams. So, the corresponding mass flow rate and Cp being known to us, we can try to calculate the what is called their heat duties, or what is the amount of heat that is getting transferred. So, there basically as you can understand that we have 2 hot fluids, they were entering at 300 and 300, and the other 3 were entering at say 180, 160 and 170. So, like this we had this arrangement of the fluid streams, and then we had these are the separating plates. I mean this was one plate 1, 2, 3, 4, and these plate numbers we have designated as this is plate 1, this is plate 2, plate 3, and plate 4, because these plate numbers are equally important, and this is plate 0, of course, this is insulated, and this is plate 5th. So, that is equals to again insulated, and but we are mostly concerned about this plate temperatures. So, if we now look into this again, as we are talking that how to take or calculate the heat duty. So, since we know the heat transfer, the mass flow rate and the Cp, corresponding Cp, it was known, it has been given in that paper, and we can calculate the heat load, and this is something called the cumulative heat load. So, if we find that the layer number 1 was fluid stream B, and then we have the fluid stream C, A and D, and we can find out what are their corresponding temperatures. So, this B actually this fluid temperature, if we go back to our earlier slide, here in this we have seen that there are 5 fluid streams. So, out of which one is that 300 and this is 300. The first fluid was B, then we had C, this is C, then we had A, and then we had again D, this was fluid D, and this was E. So, this is entering, the B entered at 170 degree 170 Kelvin, this is 170 Kelvin, C was entering at 300 Kelvin, then A entered at 180 Kelvin, and E was entering at 160 Kelvin. So, this is the repetitive block in a multiple layer. So, if it is such that this B, C, A, D, E combination was giving an optimum solution according to this genetic algorithm problem. So, we wanted to check whether if it is not always possible to get a genetic algorithm, how do we know whether this simulation is an optimum simulation, or this pattern is an optimum pattern, that B, C, A, D, E is an optimum pattern. So, for that, the criteria that we have said is that the cumulative heat transfer. So, as you can understand that this fluid is giving heat to this one. Similarly, this is a cold fluid adjacent to the hot one. So, the heat will be coming to this side, and then this is 300. So, heat will be flowing to this side and heat will be flowing to this side. So, from this fluid, this hot is supposed to give heat to this, and this is to this side, and this hot fluid is again supposed to give heat to this side and this side. Now, individually if we look at this is say Q1, then we say Q2, and then we say Q3 and Q4. So, deliberately we put all this downside one as positive. So, if it is happening other way, then it will be a negative one. So, this is the individual heat getting transferred Q1, Q2, Q3, Q4, and the cumulative is obviously their addition. So, we will have a look into that part. So, here we have the individual heat loads, as we have said that it means that between these 2, 3, 4, 5 layers. So, we have Q1 that is equals to on this side. So, that is a negative one. So, on this side this is a positive one, and that is 15. The next one is on this side, this is equals to a negative part. On this side this is again a positive quantity. So, it is downside, and this is equals to 13 minus on this side. So, we have like this different kind of heat, the cumulative individual heat load for corresponding to each plate. And now, if we just keep on adding them, 7 with 15, it becomes a positive, then this positive and this negative gives another positive, and this negative, I mean this 13 plus 26 gives a positive. Then it, when we combine this one with this part, it becomes very, I mean, negligible. So, this is, we have an energy balance of the order of this type. So, this cumulative heat load, as you can understand, that if we put with the number of layers, what is the number of layers, say 1, 2, 3, 4, 5, and they were B, C, A, D and E. So, corresponding to this, we have the cumulative heat load, and when we plot them with the number of layers, we find that what is happening, that alternative, the heat load with the number of layers, it is, if we consider it to be 0, sometime it is coming on the negative side, the very next layer it is on the positive, and then it is coming on the negative side, again it is going to the higher side and then coming back to this one. So, an indication that the simulation is correct, that it will start with 0 and end with 0, and in between this zigzag pattern, that it is coming above this level. Sometime it is according to the number of layers. When we plot, in every layer, either it has to be on the negative side, and in the next one it has to go to the positive, and then it has to come to the negative, and like that. So, this zigzag pattern will tell that this simulation or this stacking pattern is corresponding to an optimum stacking pattern. And any deviation, if in this context we have said that this was B, C, A, D and E, that was the optimum stacking pattern we have obtained from that genetic algorithm, but it is and that also shows that this cumulative heat load, when we are plotting it with the layer number, that is also reflecting the same, that this zigzag pattern in the cumulative heat load, that is also it is following. The another indication of this optimum stacking pattern is that at any cross section in the heat exchanger in a particular layer, if this is the heat exchanger and there are multiple fluids going in and out. So, the optimum fluid pattern, it may be such that you may have to put some of the streams just one above the other, I mean in the parallel combination or parallel counter combination, but it may be such that at any location, if we if the other dimension is like this, I mean this is a 3-dimensional one, and if we just cut across, I mean if we plate, if we slice this heat exchanger at this plane, and if we find out what is the temperature of the plates. So, you can understand that the plate temperatures, if we look at, we will find that these are the separating plates, and we have the inlet and the exit temperatures we have already calculated, and also we said that our simulation was able to calculate the plate temperatures. So, the separating wall temperature also Tw1, Tw2, etc., and we are able to, when we divide this entire exchanger into small number of segments, we can find out what are the intermediate plate temperatures, say Tw1 at this position, TW1 at this position and this positions like that, because this is going to vary with the length of the exchanger. This is say the Lx, and we have the other dimension. So, this separating plate will obviously, as you can understand, that the fluid temperature is varying along the length of the heat exchanger, and obviously the separating wall will also change with the fluid. Now, at any particular cross section, so that means if we take or consider this particular location, so we want to look what is the separating wall plate temperature. So, between this, what is the wall temperature, between these two point, what is the wall temperature. So, at different number of layers. So, this is say B, C, A and D and E, and we will look into the wall temperature at this, at a particular any cross section at anywhere in the heat exchanger. It may be at the middle, it may be this end, it may be on this end, anywhere along the length of the exchanger, but at a particular location when we have to compare, we have to compare say at Lx1 or at Lx2 or at Lx0 or something like that. So, we try to find out what is the wall temperature at a particular cross section of the heat exchanger, and if we find that they are more or less uniform, then we say that the stacking pattern is an optimum stacking pattern, or we can say otherwise that an optimum stacking pattern will follow this kind of temperature profile along the length of the heat exchanger at a particular cross section. So, for this situation, that example that we have shown you, it is first of all following that zigzag pattern for that cumulative heat load, and in context to in context to the wall temperature, that program was giving us the wall temperature at different locations, as we have said that those plate temperatures we have calculated, the plate temperatures we have calculated, and at different positions, say this is plate 1, 2, 3, 4, like that we have not taken the. So, there were 5 fluid, and these were the plate temperatures we have considered excluding this one. So, we have 4 temperature points, and the plate number 1 is having temperature at this, and like that we have for plate number 2, plate number 3 and plate number 4. So, like that we had temperature at different locations, and they are at a particular location, they are pretty similar. And similarly, at different, say we have actually divided this entirely into that 4 positions, and we have noted these 4 temperatures. If we go back to that original heat exchanger picture, you will find that there were 4 such locations at which all those temperatures were calculated. So, at a particular location or at a particular cross section, we find that the temperature is remaining more or less similar. It is not changing much. So, that is how we said that the this pattern is near or close to an optimum stacking pattern. So, if if it is it's not if it is not an optimum stacking pattern, then how it is getting varied, that we can see with another example. This is not, we will not go into the details of this one. As you can understand that there are 7 number of plates. So, basically we have here 6 number of plates, we have 7 number of fluid streams. So, when the fluid streams 7 number of fluid streams are arranged in a way, and they give an optimum stacking pattern corresponding to that genetic algorithm. corresponding to that situation, we find that this optimum stacking pattern is giving heat transfer along the length at a particular cross section. This is the kind of temperature at different plates, corresponding to different plates, and these are the different locations. So, what we have is more or less uniform, but if it is such that it is not, this is corresponding to the optimum stacking pattern, but if it is not, I mean, in that context we will find that the when it is deviating from the actual stacking pattern, we find that the surface wall, I mean the plate temperatures are like at particular location, this is deviating like this, and in fact this will also deviate if you calculate that cumulative heat load calculation. If we do it for this configuration also, we will find that this will also deviate from that I mean that cumulative heat to load will not have an optimal like zigzag pattern. So, this will also have some kind of pattern like this, and that will correspond to I mean a deviation also in the wall temperature or non-uniform wall temperature. So, these two I mean conditions, like one is the cumulative heat load, and the plot of the cumulative heat load with the layer numbers generally is considered as a I mean criteria for the optimum stacking pattern, and particularly in case of multi-stream plate fin heat exchanger, the temperature at a particular cross section at any location of the exchanger, that uniform temperature in the plate temperature is another criteria to call it as an optimum stacking pattern. So, this is all about the stacking pattern, and there are I mean there are rather other than this stacking pattern, often we have to design this is you may understand that, or you may realize, you might have realized that this particular when we are talking about say putting the different fluid streams, say B, C, A, D, E, and we had initially this 5 fluid streams, and we did not have any information about what would be the possible arrangements, and when we have say 7 number of streams like this, say in that case situation becomes very I mean critical to physically check exactly what are the optimum stacking pattern. So, in that case we have to go for this genetic algorithm program or some other optimization program to find out exactly what is the optimum stacking pattern corresponding. Of course, this had in particular in this problem we tried to maximize the heat transfer, and we tried to find out the layered stacking pattern corresponding to the maximum amount of heat load. So, we have to I mean this is basically a design problem. Backed and the back of this one we had that simulation program that was basically a rating problem. That means we were looking for a particular design or the stacking pattern, and corresponding to that stacking pattern what is the simulation or the outlet temperatures at I mean it is predicting, that is important. So, a combination of these both this simulation and design goes hand in hand, particularly in case of plate fin type heat exchanger. So, thank you for your attention.